Okay, today's lesson is going to be on what we call precipitation reactions. The word precipitate means a solid. So a precipitation reaction would be a reaction in which a solid forms. If you look at the equation either on the slide or it's on your notes as well, you can see that this is the reaction of a solution, aqueous, of NaCl. So this would be like table salt dissolved in water, with a solution of AgNO3, and it makes two things because of the double replacement reaction. Your Ag and Na are going to swap partners, so it makes sodium nitrate and silver chloride. The solubility rules, which again we don't have to memorize, luckily, but the solubility rules tell us that silver chloride is a solid. And then you would know, even though you didn't memorize your solubility rules, you do know that compounds that have alkali metal will always be soluble, as well as the ones that have nitrate will always be soluble. So you would have known that this would be aqueous. Now, because we're not memorizing the solubility rules, you aren't going to have to worry about identifying something as a solid, but you do need to be able to identify the product that is aqueous from your four substances that are always soluble: alkali metal, ammonium, nitrate, acetate. In all the problems that we're going to do, there will be notation that they are precipitation reactions. So once you decided that NaNO3 was aqueous, you would have known immediately that AgCl must be a solid. Otherwise, it would have been aqueous as well. And aqueous can't yield another aqueous and another aqueous, or else there's no real reaction taking place. So this example, you can see that your little image here, you've got your sodium chloride making a solution. Actually, this isn't really this exact equation, I'll tell you, because you can see them pouring solid in. But since the solid immediately becomes a solution upon entering the silver nitrate solution, it is essentially the same thing. Our example should really be a beaker here pouring NaCl aqueous in. Okay, that would be a better representation. So that's your basic precipitation reaction. Now what we're going to do with those precipitation reactions is we're going to turn them into something called a net ionic equation. If you take a look on your paper there, you'll see three terms. The first one's molecular equation. Those are the ones that you've been doing this whole time. The problem on the board right now is an example of a molecular equation. Of course we balance it because balancing is necessary, but that's a molecular equation. It shows everything just as is. You see the AQs and the S's, they don't have to technically be there for it to be a molecular equation. It's just showing what compounds are reacting to form whatever compounds are forming. Then there's a thing called an ionic equation. Now you see on your paper it says that that's an equation that shows all soluble ionic compounds as ions. So how do we know something is soluble and ionic once we've written our equation? So say we're looking at this. If you look right here, it says aqueous, aqueous, solid, and aqueous. Only the aqueous ones are soluble, hence our solubility lesson that we did before. The solid isn't soluble, so therefore it doesn't form ions. Think back to your strong electrolytes, weak electrolytes, non-electrolytes. So anything that is listed as aqueous, we are actually going to ionize. Okay, we're going to break up, just like we did in our beakers, just like we did in our little equations, but this will all be part of a big equation together. So our ionic equation would be breaking up CuNO3, so I end up with a Cu plus 2, that's the copper ion. There are two nitrates here. You see this 2 showing two nitrates, so I'm going to say 2 NO3s. Notice I'm not putting the phase back on it. You can if you want. I could write a little AQ next to both of these, but once you've established it's aqueous, now that you've ionized it, you would only ionize it if it was aqueous. So it's going to be plus. Now, this is a sodium hydroxide. In sodium hydroxide, we have one sodium and one hydroxide. However, there are two of them in the balanced equation. Your molecular equation, you always want to balance and then carry that balancing throughout. So if I'm going to write down how many sodiums I actually have 2 Na pluses, and I also have 2 OH minuses. On the product side, you see the first product is a solid. So I am not going to do anything to that. It can't ionize. It stays in its molecular form because it wasn't soluble. So I'm going to leave the solid alone. And then I'm going to break up these 2 NaNO3s. So that'll be 2 Na pluses and 2 NO3 minuses. So that is the ionic equation. Everything that was soluble and aqueous was shown broke up. Now for the net ionic equation, you're simply going to take things that appear exactly the same on both sides, and you're going to cancel them out. So if you take a look on both sides, we have 2 NO3 minuses. Those will cancel. And on both sides, we have 2 Na pluses. Those will cancel. So that leaves us with a final net ionic equation of Cu plus 2 OH minus yields Cu OH2. Now, this equation, this net ionic equation, is important for different reasons than the molecular equation. This equation is important for us to see everything that's reacting. The net ionic equation shows us what actually is chemically forming what that chemical reaction is. Remember, the definition of a chemical reaction is something that produces either a gas, a solid, or a new liquid. Okay, it has to be something like that. If it doesn't produce something new, then it's not considered an equation. So this is showing us the ions that actually precipitated out, essentially. The aqueous ones are still there. Okay, we canceled them out above, but it doesn't mean they're not there. They're just floating around in the solution. So in this solution, you would have a liquid that would be comprised of sodium ions and nitrate ions. And then down here at the bottom, you would have a pile of CuOH2. So that's the basics of it. Now, it used to be I could pretty much give you any two sets of reactants, ask you to predict the products by a double replacement reaction, and then ask you to tell me which one was the solid and which one was aqueous. But now with your limited solubility rule memorization, I'm going to have to always include on the reactant side at least one compound that contains an alkali metal, ammonium, acetate, or nitrate. That way you'll always be able to pick out the one that's soluble, that product will be aqueous, and then the other one has to be a solid. Okay, and I'll show you what I mean by that with some example problems. Ooh, you weren't supposed to see that. Oh well. That's fine. So silver nitrate has a formula AgNO3, and magnesium chloride has a formula MgCl2. Now, you may be thinking, why does she have AQ next to these right now? The reason is because the problem already told us that it was a solution. Okay? If they tell you it's a solution, that means those substances were dissolved in water. If they're telling you it's a solution, then it had to have been soluble. Okay, because if you take something insoluble and put it in water, it's not going to make a solution. To make a solution, they actually have to dissolve. So your reactants will always be aqueous. Your job is to figure out on the product side which one's the aqueous one, and then therefore which one will be the solid one. So let's do a double replacement reaction. Silver will be pairing up with chlorine, but remember we have to use our charges. So silver's charge is a +1. Silver, you can't tell its charge from the periodic table, but you should have that one memorized. So if that doesn't pop right into your head right now, please commit that one to memory, that silver is a +1. And then chlorine that it's going with is a -1. So if we crisscross those, we get AgCl. Now, if you think about that, neither one of those ions falls into our always soluble rules. You know that one of them has to be there. So chances are this is going to be our solid. But let's do the other one so you can see that it is. The other one's going to be magnesium with nitrate. So Mg plus 2 with NO3 minus 1. So when we crisscross that, we get MgNO3 2, like so. Now there's that nitrate. You see that nitrate and magnesium nitrate. That makes this one aqueous. And if this one's aqueous, then we know that one is solid. Because again, these are all precipitation reactions. So one of the products has to be a solid. So now what we're going to do is go through and do the ionic equation and then the net ionic equation. So if you remember from before, I said that anything that is aqueous, so aqueous, 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 we are going to break up. So let's do this one together. So we're going to break up AgNO3. It'll break up into Ag plus and NO3 minus. We're going to break up MgCl2. Oh, slow down. Wait. We have to balance before we do any of this. I just violated a cardinal rule, and our first equation is not balanced. So to balance it, we're going to need a 2 there, and we're going to need a 2 there. That makes a big difference because this is supposed to be 2 Ag pluses plus 2 NO3 minuses. So make sure you balance at the molecular equation step. So we get Mg plus 2 plus 2 Cl minuses. So I ionize the MgCl2. There's 2 Cl minuses because of that too, right there. Then for my product, I am not going to touch this one. Notice it stays together. Just brought it right down because it is the solid. And then MgNO3 will break up into Mg plus 2 and 2 nitrates, like so. All right, that's the ionic. Now we need to cancel things out that can cancel out. So it looks like our Mg plus 2s are on both sides, the exact same. And our 2 nitrates are on both sides, the exact same. So that leaves us with 2Ag plus 2Cl minus yields 2AgCl. These coefficients can be reduced, and you always want to reduce coefficients if you can. So that leaves us with a final answer of Ag plus Cl minus yields AgCl. Don't forget your charges on the left side because those are ions. You can't just say Ag plus Cl. It's Ag plus Cl minus yields AgCl. So you're going to write your equation out. You're going to predict your products. You're going to figure out which one's aqueous, therefore the other's a solid. Then we're going to ionize all the aqueuses, cancel things out that appear the same on both sides. By the way, the name of those guys that cancel out on both sides, they're called spectator ions. Spectator ions. It's actually on the front of your notes paper down at the bottom. And they're called spectator ions because they're considered to be just watching what's going on, just like spectators at a football game. All right, so let's try another one. Once again, I'm ruining the excitement here because I did not cover up the correct part. So let me do that real fast there. Oh, see? I know you can rewind it and look at it. Don't. All right, take a second and write out the formula for ammonium carbonate and calcium chloride. Notice both of them are solutions. They always will be. So you're going to put AQs next to them. You can pause the video now. And then we'll go through and see what those formulas look like. So you should have written parenthesis NH4, parenthesis 2CO3 aqueous, plus CaCl2 aqueous, yields. Now we have to do our double replacement reaction. So we're going to get NH4 with chlorine. That's going to make NH4Cl, because again, NH4 has a +1 charge, chlorine has a -1. And see that ammonium there? I immediately know this one is aqueous. So that's good. And then calcium is going to go with carbonate, like so. Crisscross those, you get Ca2CO3, 2, but we can't have those 2's, so they'll cancel off to give CaCO3. And that one must be a solid, since we already determined that the other one was aqueous. Now, before we do anything else, we need to balance. So I'm going to put a 2 here, and I believe that takes care of it. Okay, so there's our balanced equation. Is it balanced? Yeah, balanced equation. Now it's time for a net ionic equation. So we're only taking the ones that are aqueous. So this one, and this one. Now I want you writing the aqueous and the solid in the molecular equation, but you don't have to write it past here, okay? Because once you start breaking them up, then you're accounting for the fact that they are aqueous. But in the molecular equation, you need to have those AQs and S's written. So let's start to break this up. So right here, there are 2 ammoniums. So I'm going to go 2NH4 plus CO3 minus 2 plus Ca plus 2 plus 2 Cl minuses yields 2 NH4 pluses and 2 Cl minuses. Again, I'm using that coefficient. There's one of each in here, but there's 2 of those compounds. And then plus CaCO3, which is a solid, so I'm not breaking it up. I'm going to cancel things out that can cancel. So NH4 pluses cancel and 2 Cl minuses cancel. And that leaves me with my final net ionic equation. Like so. Again, notice my charges are still there. Don't lose those charges. They need to be there. But this shows the precipitation portion of the reaction. Okay, let's try another one. All right, so do your formulas. Go ahead and figure out the formula for iron 2 chloride and then potassium sulfide. Hit pause while you do it, and then you can come back. So the formula for iron 2 chloride is FeCl2, and it's aqueous because they told us it was a solution. And then the formula for potassium sulfide is K2S, and again, aqueous. Now we're going to do a double replacement reaction. So iron's going to go with sulfur. Now the iron, they already told us, was iron with a Roman numeral 2. So it's got a +2 charge, and sulfur has a -2. So when we crisscross and reduce, we end up with FeS. Okay, it would have been Fe2S2, but it's ionic, so you have to reduce. Now neither one of those falls into our rules. So can you guess what it might be? Most likely it's going to be a solid. Let's go ahead and do the other one to confirm. So we end up with potassium and chlorine coming together. So potassium's +1, chlorine's -1. That'll make KCl. You see that alkali metal, group 1A metal right at the beginning. That means it will be aqueous. So that tells us that this one is a solid. Again, find the aqueous one, and you know the other one's a solid. I need to balance. Usually these are pretty straightforward balancing. You usually don't have to use the math way to balance, but if you need to, go right ahead. So that's our molecular equation balanced with the labels of aqueous and solid. Now I'm going to do my ionic equation. Actually, you might pause me right now and go through and do your ionic equation for yourself, and then your net ionic equation, and see if you've got it right. All right, so what you're going to do here is take and break up the aqueous. So Fe +2, and then 2 chlorides. I knew there were 2 because of that little subscript. And then K2S, I'm going to have 2 K pluses and a sulfur -2. And then FeS is a solid. And then 2 K pluses plus 2 Cl minuses for the 2 KCls once they ionize. Now 2 KCls cancel. 2 K pluses cancel. That leaves us with Fe +2 plus S -2 yields FeS. Again, net ionic equation showing the formation of a solid. So that's pretty much the basics of net ionic equations. They're going to be important. We're going to use them in a lot of different facets. Again, the molecular equation is great. This first equation right here is a great equation. Well, wasn't that interesting? Sorry. It's a great equation for showing certain things. Okay, it shows us what compounds reacted. It shows us both products that formed. But we write this net ionic equation to actually see the precipitation part of the reaction, to only focus on the ions that are actually forming the solid. So it's a little bit different of a viewpoint, really, is what it's coming down to. So you're going to have some practice problems for this to work on for tonight. Again, look for those aqueuses. The reactants will always be aqueous. On your product side, you'll be able to find one of the aqueuses using our always soluble rules, and then whatever the other one is will be a solid, and then you can go forward from there. And we will